您直接开始就可以了，然后我就不再做提醒了。
Okay, I guess it's time. So, good evening, ladies and gentlemen. It's my great pleasure to host the Charles Park course series again. Today, we are honored to have our distinguished guest speaker, Professor Jie Xu, to give us a lecture on the topic of Edge AI for ISAC. Professor Jie Xu is currently a tenured associate professor with the Chinese University of Hong Kong, Shenzhen, and the Shenzhen Future Network of Intelligence Institute. His research institutes include wireless communications, edge intelligence, and integrated sensing and communications. He is the chair of the IEEE Wireless Communications Technical Committee, and the vice co-chair of the IEEE Emerging Technology Initiative on ISAC. He has served as an associate editor-in-chief of the IEEE Transactions on Mobile Computing, and editor of the IEEE Transaction on Wireless Communications, Transaction on Communications, and the guest editor of the IEEE Journal on Selected Areas in Communications. He was a recipient of the IEEE Signal Processing Society Young Author Best Paper Award, the Communication Society Asia Pacific Outstanding Young Researcher Award, and the Wireless Communications Technical Committee Outstanding Young Researchers Award. He's an IEEE Fellow, a distinguished lecturer of IEEE Communications Society, and a collaborative, highly cited researcher. Okay, before we start, please just allow me to a little bit advertise a little bit for this conference, IEEE conference on ISAC, which will be held next year. It is the first large event dedicated to integrated sensing and communications and its applications. It's jointly sponsored by three IEEE societies, including the ComSoc, SPS, and AES. We're currently calling for papers, and the deadline is in June 2026. You can submit your paper via this link on the bottom of this page. Okay, let me return the microphone to today's guest speaker, Professor Xu. Please.
Okay, thanks, Yifeng, for the kind introduction. So let me share my screen. Okay, so thanks, Professor Xiong, for the kind introduction, and thanks for Professor Liu Fan for organizing this course series, and also thank the Task Park to give us this valuable platform for share our research. So I'm Jie Xu from SSE, the CUHK, Shenzhen, and also the Shenzhen Future Network of Intelligence Institute. So today I would like to talk about ISAC meets Edge AI, so the intelligent sensing, communication, and computation at network edge. So to start with, let's look at integrated sensing and communication. So I think the audience has been getting familiar with this concept because we have several distinguished speakers talking about this concept. So basically, ISAC corresponds to the design paradigm and the corresponding enabling technologies combining sensing and communication systems. So the compilation can lead to two benefits. One is that we can enhance the utilization efficiency of resources. And the second is to pursue the mutual benefits between sensing and communication. So strictly speaking, and I think in most of the lectures previously discussed, so we mentioned ISAC as a reuse of wireless signals for the dual purpose sensing and communication. So we're gonna use the unified wireless signals for the two purposes at the same time, or we use sensing for communication or communication for sensing. So recently, ISAC has already been recognized as one of the key usage scenarios for IMT 2030 towards the 6G networks, and also in Wi-Fi. So the 802.11bf has been already the first international standard for ISAC. So we see ISAC will be quite promising for our future wireless systems. So let's look at what we have done in the ISAC research in the academia. So so we classify the conventional ISAC study in the following aspects. So the basic model for ISAC study we call the monostatic and the bistatic ISAC systems. So which means that we're going to use one single ISAC transmitter a transceiver to reuse radio signals for both communication and sensing at the same time. So in this case, there are many fundamental issues to be discussed. So for example, right, I know Professor Xiong and Professor Liu have done many interesting work on the fundamental information theoretical performance trade-offs between communication and sensing. Because the wireless signal are reused for two purposes. So there fundamentally exists a trade-off between the performance of the two. So how to characterize the fundamental information theoretical limits is an important issue. And based on this, we can design the system for enhance both systems' performances, or we try to optimize one system's performance while subject to the performance limit for another. So we can do the transmitter waveform design. We can also have a transmitter waveform design, and we can do beamforming optimization and the resource allocation. And more recently, people start to looking at the network ISAC, which means that we can utilize network nodes in the cellular network, including base stations, user devices, and also some new components like intelligent reflecting surfaces to cooperate with each other in both communication and sensing. So I believe that the ISAC, the benefit of ISAC as compared to other sensor modalities is that all the devices are naturally connected with each other. So we can, using the collaborative sensing to sense a large area. And in this case, how to do the nodes synchronization and how to do the collaborative signal processing are important technical issues to be handled. And we also have the sensing assisted communication, so which means that we try to exploit the wireless sensing information to facilitate the communication system design. For example, we can use the sensing data to facilitate the accretion of channel state information. And furthermore, I know the security and privacy issues related to both sensing and communication are quite important. So in recent years, researchers from, I think mainly the Communication Society has done a lot of work along these research directions. But we notice that there are some limitations. Because in these researches, we normally focus on some simplified sensing tasks. For example, we assume the target to be a point target, and we can do detection, estimation, and this kind of tasks. But in practice, right, so we have many, we have more complicated tasks. And also in this research, we normally use model-based signal processing approaches to facilitate the design, okay? But if we look at ISAC, so actually we can look at it from a more broader perspective. So in this case, so we also know that nowadays we have many different types of sensor modalities. So we have vision, we have a LiDAR, and we have for example, millimeter wave radar. So actually ISAC, if from a broader perspective, we can view ISAC as a case when wireless communication systems, which interconnect distributed multimodal sensing nodes to enable collaborative multimodal sensing. So in this sense, so our discussed wireless sensing can be viewed as a technique to complement and enhance the capability of diverse sensing technologies. And in this case, we can enable many ISAC use cases. For example, we can do activity detection, movement tracking in smart home. We can also do 3D imaging and scene reconstruction. So in the scene reconstruction, the ISAC signals actually can provide the depth information to facilitate the 3D scene reconstruction. We can also do automotive navigation in intelligent transportation systems, and also we can have UAV detection under condition avoidance for the low altitude economy. And more recently, we're also focusing on how to construct the digital twin for wireless channel. We call it a channel knowledge map, and some people call it a radio map. So we can also use multimodal sensing information to facilitate the construction of these kinds of channel knowledge map. So for all these applications, we notice that the conventional model-based optimization design may not be able to handle such complex sensing and ISAC tasks. So in this case, we notice that AI is becoming more and more popular. And in this case, the rise of large models actually drives the translation from specialized AI to generative AI, which can enabling better generalization capabilities. And furthermore, for sensing and communication tasks, we can also utilize advanced AI models. For example, we can use the most advanced Gemini 3, or DeepSeek, to fine-tune these models to get to address the downstream tasks like sensing and communication tasks. So in this case, the integration between AI and communication networks has been recognized as another important usage scenario towards 6G. So due to the advancements in edge computing, we are actually moving from the centralized cloud AI to distributed edge AI, because at our network edge, we have enhanced compute and also a large number of sensing data. So in this case, the convergence between AI and the networks has enabled two paradigms. One is AI for network, which means that a communication network are shifting from the traditional model and optimization-based design towards the joint model and the data-driven design assisted by AI algorithms. On the other hand, we have networks for AI, which means that the network should be evolving from the current one that dealing with data transmission to handle various AI training and AI inference tasks. So our network design objective should also be involved from rhythm maximization towards the task-oriented optimization. So in this sense, we believe that edge AI can offer as a powerful means to manage complex sensing and ISAC tasks, and also advance the ISAC capabilities. So the synergy between ISAC and edge AI has transformed the wireless networks from the conventional data transmission network towards an intelligent multifunctional network, integrating sensing, communication, computing, and also AI. So you see that at the network edge, many IoT devices, ISAC devices, and various sensors to perform the network sensing. And at the base station, which may serve as edge and the cloud servers to compute and process this data. And also, you can download or upload the data and AI models between the devices and edge servers. So wireless communication between gonna play an important role to connect the compute and the sensing to realize many AI functionalities. So we can also we can see the integration between ISAC and edge AI also gonna lead to mutual benefit. On one hand, we have edge AI for ISAC. This means that we can use AI algorithms and edge computing to process the massive distributed sensing data. to support the ultra low latency and high precision perception requirements. And on the other hand, we can utilize ISAC to facilitate the edge AI. On one hand, the sensing can provide massive, timely, and high-quality information to support training and inference. On the other hand, the high-speed and low latency communication can help enhance the cross-load collaborative edge learning and edge inference. So in this talk, we're going to focus on the synergy between ISAC and edge AI, but in this case, there are multiple technical challenges to be handled. So the first challenge is that for specific sensing and ISAC tasks, how to design proper AI models. So the design of AI models can either be trained from scratch, and also we can utilize the advanced foundation models. So we can use fine-tuning to adapt them to specific tasks. And on the other hand, we have we need to design the model training and the fine-tuning at the network edge. Okay, so we face two challenges for the training and the fine-tuning. On one hand, the data is distributed at the different devices, and the data will be long IID. So the long IID data distribution may make the global model alignment and the stable training difficult. On the other hand, we also face the scalability and the efficiency issue due to the limited computation, memory, energy, and communication resource at distributed nodes and base stations. And another issue is model inference. So when given the well-trained model, we need to perform various inference tasks at the network edge. So different from cloud inference, so the resource is also limited in this case. So how to perform low latency and reliable inference tasks by using the distributed limited resource is another challenge, especially for some ultra low latency tasks. So in this talk, I think there are many open problems along these directions. So in this talk, we will only focus on several of our current works. We just done some preliminary works to partially address these challenges. So the first piece of work we try to talk about is how to use fine-tune the LLM, the natural language model, to facilitate the sensing-assisted communication. In particular, we focus on how to use sensing to get the channel state information for communications. So let's look at the task first. So we know that in wireless communication, for example, in MIMO beamforming, so how to get the channel state information at the transmit side is particularly important. So conventionally, we use pioneer-based channel estimation to get the channel state information, right? So in this case, the base station can transmit pioneer, and the pioneer can be used to channel estimation, and then the receiver can feedback the CSI to the transmitter. So we know that when the channel dimension become large, for example, we have a ultra wideband transmission in millimeter wave and terahertz. We also have the ultra massive MIMO, right? So in this case, so we can use compressive sensing and the different types of methods to recover the CSI with reduced number of pioneers. And another method to get the channel information is to exploit the spatial and the time correlation between the channel to do the channel prediction. So the idea is that we can use historical CSI to facilitate the prediction of channel in the future, okay? But in all these techniques, right, we didn't take into account the sensing message or sensing data. So the sensing actually can provide the following information to facilitate the CSI accuracy. On one hand, the sensing information may identify the environment information. For example, the scatters in the environment and or the multipath information in the environment. So in this case, we can get the environment-aware learning to get the CSI, and also we can track the dynamic targets in the environment, which can also help us to get the multipath information for communication. Okay, so we can look at this example. We can look at the correlation between communication and the sensing channels to see the motivation more clearly. So in this case, suppose that the base station, the ISAC base station is doing the monostatic sensing. They're going to transmit the message and use the echo to sense the environment. At the same time, it is transmitting information to a mobile user. So in this case, you can see that in the environment, the channel actually consists of many multiple passes, and we have different scatters contributing to different multipass. So you see that we can classify the scatters into 3 types, which corresponds to shared scatters, which means that, for example, for this scatter, this is shared scatter, which means that it's not only contributing to the communication channel, but also contribute to the sensing channel. And we also have the communication scatters. For example, for this one is far away from the ISAC base station. So in this case, there is no, it does not contribute to sensing, but only contribute to communication. And also we have the sensing scatters, which means that the communication link is blocked by some obstructions. So in this case, the different, we can see that the sensing and the communication channel for the shared scatters can share some common parameters, including the Doppler shift f, and the angle theta, as well as the angle actually is, we have elevation and the azimuth angle. Okay, so in this case, this means that the sensing information actually contains useful information to facilitate our communication design. So this will be the detailed model. So you see that they share some common parameters. And we just do some experiments. So we use Seona from NVIDIA, and we just generate the environment, and we generate both sensing and communication channel. So we just look at the angle distribution of both communication and sensing channels. So we do this experiment to verify our observation that there may exist some shared scatters, which contributing to both sensing and communication channels. So in this case, right, we can exploit the sensing message or sensing information to facilitate the communication CSI. And in particular, we're going to look at a CSI prediction problem in a complex environment. So the channel prediction problem is formulated as follows. We try to construct a temporal correlation model, which can use the historical CSI, which is HCI, to predict the future channel HCI from I equal to t+1 to t+q. And conventionally, they didn't take into account the sensing information. And if we take into account the sensing information, the problem is rewritten as follows. And you see that the capital HSI is added as additional information in the prediction. So the main idea is that sensing information can identify the K scatters, locate dominant passes to facilitate the communication CSI prediction. So if we look at the existing methods, so normally people can use model-based methods, and in which we're going to use statistics models to predict the channel state. So in this case, we normally have simplified the assumption about the environment or about the channel, which can be difficult to use for complex and dynamic multipass environments. And the other commonly used is deep learning methods. So in the conventional deep learning methods, we're gonna use the labeled data to train a neural network from scratch. So then we can use the deep learning methods to predict the future channel. But notice that this model highly depends on the training data and the likes generalization, and also it's going to struggle with how to model the complicated spatial, temporal, and frequency correlation. So in this case, what we do is that we're going to rely on the LLM. So the benefits of a LLM fine-tuning based design over the traditional DL methods are following. So first, because LLM is actually a pre-trained model, it has been pre-trained on massive knowledge. So in this case, by using LLM fine-tuning, we can just use a limited number of training data. We use few short learning. We can get satisfactory performance. And the next benefit is the generalization. So in this case, the LLM-based design can have a strong cross-environment generalization due to the benefits of pre-training. And on the other hand, the LLM-based model can better handle the multi-modal data. For example, in this case, we're going to combine the sensing information and the communication information. Although they are both CSI, but they have different dimensions. So how to unify them, the LLM also can play a beneficial role. So in this case, we design a fine-tuned LLM model for the sensing-assisted channel prediction. So we have the backbone LLM here. So actually, in the experiment, we use a small, not so large LLM, or we use GPT-2 as a backbone LLM. So we're gonna frozen most layers, but before the LLM, we just add a preprocessor and the feature extraction and the fusion components, because we need to process the sensing CSI and the communication CSI and combine them together to tokenize them to feed into the backbone LLM. And at output, we also we convert the output features of the LLM into the final prediction results. Okay, so in this case, we can look at some experiments. So in the experiment, we just generated the channel, the communication and the sensing channel based on NVIDIA Sionna. So we just generate a real environment and use Sionna to get the channel, get the CSI. And we use part of the CSI to training and another part for testing. So you can see that we compare the performance on the different user speed and on the noisy historical CSI case. So you can see that if our training data is limited, so in this case, the LLM-based design approach can predict the channel and adapt to different scenarios quite fast. So you see that the performance over the conventional LSTM and the CNN-based design are quite significant. Okay. So in this simple work, we just show the benefit of using a fine-tuning LLM to do the sensing-assisted communication. And in the future, I think how to extend for multimodal sensing-assisted communication by incorporating, for example, vision, NIDA, and for example, the channel knowledge map will be interesting research directions to pursue. And next, we can also use design the LLM fine-tuning for wireless sensing. So this is a result from the recent SDP sensing challenge at MobiCon. So we focus on the wireless sensing task. So in this sensing task, we aim to utilize wireless signals, especially the Wi-Fi CSI signal, to sense the object. And in this case, we try to realize the non-contact detection for targets presence, location, posture, and even behavior. And the existing methods are mainly based on single processing or traditional DL-based approach. As we explained before, this methods has certain drawbacks, right? So in this case, we can also fine-tune an LLM to as an effective mean to overcome these limitations. So in particular, we're looking at a Wi-Fi-based multi-room presence detection problem. So the problem aims at identify human presence by analyzing the pattern change of Wi-Fi signals. So here are the setup. So there are one Wi-Fi transmitter. This is a primary AP, and we have two slave AP, AP1, AP2. And we're going to provide two links, link A and link B. So we're going to use the CSI connected from the two links to detect the presence of human at the three rooms. So we have room A, where slave AP1 locates, and room B, in which slave AP2 locates. Okay, and this is a living room. There's no slave AP in this room. So we need to use the two links information to detect the presence of a human in the three rooms. And also, we consider there are some interference in the CSI. For example, we have a green plan and we have a fine, which is gonna the move of the green plan gonna introduce some interference for the received signal. So here is the problem. So we have some conventional design. So conventionally, we use mainly use a deep learning based approach. So and also the design can connect some labeled data. For example, we should allow the data to be labeled, and then we connect the labeled data. We use some detection algorithms. For example, we can construct a classification network to detect the absence or presence of humans in the rooms. But however, these designs have the following two limitations. So first, it's gonna rely on the labeled data. And the second, it can difficult to be generalized to different scenarios. So based on this, we try to have some new methods. So our idea is that we try to use the unlabeled data because we have many base stations and many access points in the Wi-Fi systems, and these access points can connect many unlabeled data. So we try to use the unlabeled data to facilitate the human presence detection by using the fine tuning of LLMs. So we try to use the extensive unlabeled data to capture the environment statics. So we try to use the information to get the static environment characteristics. And then by using these characteristics, we can accordingly make a predictions on the CSI features if we assume that there is no human absent or when the environment is static. And based on the prediction when the human is absent, we can compare the predicted features versus the actual features. So if the features are quite different from each other, then we can determine that the human is present in the room and absent vice versa. Okay, otherwise, okay. So furthermore, right, because we use the fine-tuned LLM on large models, so in this case, this design can achieve cross scenario generalization. So this is the benefit. If you look at the following two pictures, the first one corresponds to the scenario with without a human absence. So you see that the CSI actually is quite the CSI magnitude actually is quite stable. But if there is a human in this, a human appears in the room, so you see that the human presence can introduce singular fluctuation during this time. So based on this, our overall algorithm pipeline is introduced as follows. So we connect the raw CSI data, but notice that there is no need to label the data. So in this case, we're going to do some feature extraction, and we're going to get two types of features. One is interpretable physical multi-path components, and another one, we're going to use PCA to reduce the dimension of the CSI. So based on the unlabeled features, we put them into LLM. So notice that in this case, we use the so-called no-rank adaptation to adapt the LLM for our specific CSI prediction task. Okay, so we're going to have a feature extraction here, and we're going to add a low-rank matrix to be fine-tuned. And notice that the backbone LLM will be frozen. So notice that in this case, the number of parameters to be fine-tuned are quite limited. Okay, so in this case, the output will be the predicted feature for CSI. And based on the predicted feature, so we put it here, and we do the feature comparison, and accordingly, we can determine whether there is a human presence or absence. So the feature extraction is an important component for our bulk pipeline. So we have this hybrid CSI feature extraction. So we combine the physical multi-path components as well as the data-based, PCA-based features. And by combining the two features, we try to have the most temporal frequency channel characteristics. Okay, so we have some experimental results. So notice that all the results are connected from the commercial Wi-Fi access points. So the data is released in the data platform, the sensing data platform. So you can see that this data platform actually provides many real-world sensing data and which can be used for wireless sensing research. Okay, so based on the data, we look at the cases. So there are some samples of link A and link B CSI data. So you see that we can use our method. You see that because you see quite a large fluctuation in this link A, right? So you can detect that actually we have some human in the in room A, and there is no human in room B because actually the fluctuation of link B may be caused by the humans in the living room. So we because the testing data are actually labeled, so we compare the predicted results and the test data, the ground truth. We see that our proposed design can achieve quite high accuracy for the multi-room human presence detection. And you see that as compared to the case without any interference, the interference caused by the grand plant and the fine and the rubber vacuum actually is marginal. Okay, so the performance degradation is quite limited, is relatively small. So from the above simple example, we show that actually large models are quite useful for any sensing tasks. But our currently considered tasks are still simple, right? So in the future, we can look at multitask problems. For example, right, we can do multitask sensing, and also we may incorporate sensing tasks and CSI prediction tasks and the different types of ISAC tasks. So in this case, how to utilize wireless data as well as some multimodal data is an important task. And also for edge side deployment, the size of the model and also the speed of inference is important, right? So we need to optimize the model architecture by using, for example, pruning or compression is also an interesting task. And another one is the sensing data set. So as compared to vision or LiDAR, so for our wireless sensing, there is still not so sufficient data can be used for our research. So I think the data platform is an important platform. So I think if the researchers you have connected any new data, so you can also share your data in this platform. Okay, so far we introduced two works about using AI for sensing and sensing assisted communication. Then another task is how to train the model at the edge, right? So in this part, I would like to introduce a new training method to enhance the communication efficiency called over-the-air federated edge learning, and we try to integrate sensing, communication, and computation for this design. So let's look at what is federated edge learning. So the basic idea of federated edge learning is to train to enable distributed edge nodes. For example, many devices, they have their local data, local sensing data. Either the data can be pre-stored at the device themselves, and also it can be connected from real-time sensing. So we try to use the locally connected data to train a shared AI model to realize some sensing or ISAC tasks. So the benefit of FEL is that it can enable the privacy preserving and the scalable collaborative intelligence. And also, if we try to fine-tune LLM, we can also use federated learning to integrating it with NORA to enable communication efficient fine-tuning for LLMs. So the idea of federated learning is to solve a minimization problem. So we try to minimize a loss function for the AI model. So we suppose that W is the parameter of the AI model, or the parameters to be fine-tuned in the LLM. Okay, we try to minimize this one. So the idea is that we're going to implement the minimization problem in a distributed fashion. So first, the edge server going to broadcast its global model to all the devices. And then after getting the global model, each device gonna compute the gradient of the loss function, and also and then gonna upload the message to the edge server. Okay, so you can see that by iteratively do the global model downloading and the local computing and uploading, you can solve this problem to get optimized AI model. So you see that the federated learning at the edge faces so-called communication bottleneck. So you see that following the process, right, you do the broadcasting model broadcasting, and local computing of local models, and then you need to upload all the model to the edge server. So you see that when the number of edge devices increases, because at the edge network we have a large number of edge devices. When the number becomes large, then the communication bottleneck is going to increase proportional to the number of edge devices. Okay, so how to reduce the cost is a challenging task. So in this case, we try to leverage the so-called over-the-air computation to reduce the communication cost at step 3 for the communication. So what is over-the-air computing or air comp? So the idea of air comp is to realize the so-called wireless data aggregation over the multi-access channel. So suppose that we have multiple devices, and each device have a certain data to be transmitted to the edge server. But different from conventional communication, the edge server tries to compute a function of all the data instead of getting individual data of each device. Okay, for example, in the previous federated learning case, edge server is going to try to compute the average of the gradient or model for each devices. So in order to get the average data in conventional design, we see that the conventional design is a separate communication and computation design. So all the devices going to transmit individually to the edge server. So they're going to use orthogonal time by using TDMA, or orthogonal frequency by using FDMA or OFDMA. Okay. So in this case, the overhead is going to increase proportional to the number of devices. But you look at the multiple access channel, actually, the signal can naturally combine at the receiver side. So the idea of air comp is to allow all the devices, all the transmitters to send the information simultaneously over the same time and the frequency resources. Then at the receiver side, as long as we can control the precoding and the decoding at the receiver side, then we can make all these symbols kind of added coherently. Okay, so in this case, the inter-user interference conventionally is harmful, that can be harnessed as a beneficial factor to enable the distributed functional computation. So in this case, air comp can significantly enhance the transmission efficiency because the K devices can only use one single time frequency slot to finish the computation at the receiver side. So we can reduce the cost from K to 1. So we can look at the basic principle mathematically in this case. So suppose that each device has Z1 to ZK to be transmitted, and after preprocessing, we will get the transmitted signals will be S1 to SK. So they're going to send the S1 to SK, and at the receiver side, they're going to receive the signal as follows. So we're going to have the received signal correspond to the summation of SK. But notice that we have some coefficient in front of SK. So the coefficient corresponds to the transmit power and also the channel coefficient. So notice that here we assume that the coefficient is real because we assume at the transmit side, it can compensate the phase difference among different devices. And in this case, we can combine the signals and also with some additive white Gaussian noise. So at the receiver side, we can just divide it by a certain parameter. We call it a denoising factor. Okay, then we can get the desired message. But notice that the desired message kind of faces two distortions. One is caused by the misalignment of magnitude, and second is caused by the noise. So this kind of over-the-air computation or air comp actually can compute a class of more nomographic functions beyond the simple computation. So typically we can do the arithmetic mean, weighted sum, geometric mean, or Euclidean norm. So from this picture, you can see that the basic idea is that we can do certain processing at the distributed devices, and we can also have a post-processing, and accordingly, we can transform the linear combination or sum operation as desired function values, for example, the geometric mean in this case. Okay, so in this case, you see that over one transmission, we can finish the summation or the function computation. So based on this idea, we can utilize it for the over-the-air federated learning. And for the over-the-air federated learning, as compared to the conventional federated learning, the main difference is that we're going to use over-the-air computation to realize step 3 for the gradient or model uploading to the edge server. So you see that each device is going to compute its local loss function and get the local gradient. And after that, they're going to directly send the local gradient information to the edge server. So you see that the edge server gonna directly process or receive the signal at the baseband without digital decoding. And in this case, we can get the weighted sum of the signal, okay, distorted by noise and some misalignment. So in this case, we can update the signal directly by yn divided by k, and then we can start the next iteration. We can broadcast the updated model or gradient to the local devices. So in this case, we significantly reduce the communication cost from k to 1, but the drawback is that the over-the-air computation is going to introduce non-uniform channel feeding over devices and also the noise perturbation, which may degrade the learning performance. Okay, so we do some convergence analysis. So convergence analysis is normally used to analyze the performance of federated learning or machine learning systems. And in this case, we're using the so-called optimality gap as a performance indicator, which means the mean value of the loss function after n rounds of communication or training, and the difference of the loss function minus the minimum value of the loss function. So you can see that after n rounds of iteration and under the certain model assumptions, such as the smoothness or bounded gradient variance, okay, under these assumptions, we can get an analytical model or upper bound for the optimality gap. So clearly, you can see the effect of over-the-air computation errors in this convergence. Okay, so we assume that the error corresponds to 3 parts. One is error flow. So the error flow corresponds to the bias of the error comp error. And also we have the initial optimality and also the gradient bias or MSE related errors. So based on this model, we can design our over-the-air computation over time. And we optimize. So in this case, this is an interesting problem. So instead of maximize the rate, we're going to directly minimizing the optimality gap by optimizing the power control over distributed devices. So you see that in this case, the power control can actually accelerate the over-the-air compute, can accelerate the federated learning. So you see that as the number of communication rounds become large, the loss value become less, and also our test accuracy outperform existing designs. So far, we consider the case when the data set are locally pre-stored at the devices. And for ISAC, right, in ISAC, we need to handle some sensing data that may be a streamed data or maybe connected in real time. So in this case, we're going to consider the integration of ISAC or sensing into the over-the-air federated learning. So in this case, we're going to have integrated sensing, communication, and computation design. The system is going to become more complicated, and we can have more degrees of freedom to optimize, to enhance the performance. So the key difference for this design from the previous airfield is that we're going to have a real-time sensing data at the devices, and in this case, each device need to allocate certain time, frequency, and also energy resources to do sensing. Okay, so that's the main difference. So I would like to skip the detail. So based on the sensing model, we can also do the similar over-the-air computation and also local training, as well as model and gradient update. So in this case, we can extend the previous analysis, okay, to the ISAC enabled airfield. So in this case, we use the loss decrease per round as a loss function to be optimized for our design. So we can see that from this loss function, okay, you may skip the detailed derivation, but I would like to talk about some insight. So the insight observed from this one is that actually it contains the information related to both L-comp aggregation distortion, that is similar to conventional L-fair, and also we have the sensing distortion related to the sensing design. So in this case, we see some interesting trade-off. So on one hand, if we allocate more resources to sensing, then we can spend more energy and more time. But in this case, the benefit is that we can enhance the sensing SNR, and also we can get more training batch or more training sensing data. But drawback is that the computation time and the energy would be reduced. On the other hand, for communication, right, for L-comp, we can allocate more energy and more time to L-comp to enhance the L-comp SNR, but at the same time, you're also going to reduce energy and time for computation. So in order to optimize the performance for the federated learning system with real-time sensing, so in this case, how to balance communication, sensing, and communication, okay, is important. So we just do the joint design, and we do some experiments based on a simple wireless sensing task. And you can see that the proposed design with integration of 3 functions can achieve the best performance. So also, right, along these directions, there are also many interesting problems. For example, right, how to do the over-the-air federated fine-tuning for large models, even with the adaptive sensing. And the second one is how to extend to the multi-model ISAC. In this case, the data at the different devices, okay, may be highly correlated. So different devices may need to collaborate in finishing one single task. So in this case, we may need to utilize the vertical federated edge learning. And another scenario is when the network becomes much larger. Okay, so in this case, a single base station or single edge server may not be able to cover the whole network. So in this case, we may need to implement the hierarchical federated edge learning over the device edge cloud networks. So the next topic I would like to talk about is edge inference. Okay, so we try to implement the inference based on a trained AI model at a network edge. So we look at the edge inference task, right? So the basic idea of edge inference is to implement the trained AI models, and we're going to do the real-time inference by using directly using the edge devices. So we can have many different types of tasks, right? So today we focus on wireless signal processing to do wireless sensing. For example, we can use CSI for human presence detection. And we also have some other tasks, right? Computer vision or speech or audio processing. And also we may need to process multi-modality signals. Okay, so let's look at the conventional design. So in this case, the conventional design, the whole information flow for the edge inference is that we're going to have a sensing data. We have sensing data at the devices or sensors, but the compute is at the edge. So we need to send the information, send the sensing data to the model, okay, to the AI model, and then the AI model going to compute the result, which is going to send back the results for the edge devices. Of course, we can deploy all the model at the edge device, which we call it edge inference, right? But also we can also split the big model at both sensors and the edge, which we call it a split inference. So for both cases, right, we face the information flow as follows. So we have a sensor here, which gonna get the raw data for sensing, and we're gonna do computation and communication. Okay, so this is wireless channel. So we're gonna do so normally, right, conventionally, we're gonna do a separate sensing, communication, and computation design. We have a separate source coding, separate channel coding, then modulation, and then we're gonna pass in through wireless channel, and then we do decoding, or channel decoding, source decoding, and then we do the AI inference by using AI models. Okay, so this kind of design is highly inefficient. First, we need to transmit high data volumes because the raw sensing data, right, normally is with high volume. So in this case, the limited bandwidth of the channel may reduce distortion in raw data and result in significant errors for AI inference. And the second drawback is the lack of task-aware design. So you see that the objective of the whole communication system is to recover the data, no matter the raw data itself or some compressed data. So at here, right, you just recover the data, but notice that for AI tasks, different information bits may have a different importance. Okay, so the conventional separate communication design cannot differentiate the importance or semantics of the information, which gonna result in resource waste. So what we do is that we can utilize the idea of semantic communication or task-oriented communication to realize the edge inference in a more efficient way, which gonna lead to integrated sensing communication and computing over the information processing pipeline. Okay, so notice that although we also call it as ISCC, okay, integrated sensing communication computation, but the key idea is different from the federated learning. So federated learning mainly focuses on the resource allocation because they share the common resource. But here, we need to design the whole pipeline towards one single objective. So the benefits of semantic or joint source and channel coding based design we have several benefits. The first one is that we can more efficiently utilize the bandwidth because we only conveying the important information or meaningful information relevant to the task. And the second one is that it may be more robust against the noise or interference, especially when the bandwidth of the channel is limited. And we also can reduce the redundancy, and also we can have the task-oriented communication where the whole design is tailored towards the task the system needs. Okay, so in this case, we believe that by using semantic communication, it can be a viable solution to enable faster, more compact, more robust, and more customized sensing. So I know that there are many interesting works about semantic communications. So we just do some preliminary research. So in particular, right, many existing works focusing on the separate, the single task semantic communication. For example, we can have a recovery task or recognition task. So conventional design actually, the design is towards one single task. So how to design a unified model for both tasks, for both data recovery and recognition, right? Is an interesting, for example, classification is an interesting problem. Okay, so this also the conventional design, because the network may be trained at a given channel condition, so it may perform poorly under different channel conditions. So our objective is to design a unified model supporting multiple downstream tasks, including data recovery and classification, and it can be utilized for variational channel conditions. So notice that in this case, we focus on a vision task. Okay, we didn't consider value sensing. So we suppose that the input are some images, and based on the image, we try to perform two tasks. One is to recover the image, and the second one is to have some classification task. So we try to design a joint source and channel coding network. So we have a deep neural network for joint source and channel coding. And then we're going to transmit a message. And the receiver side, we have two different networks to do data recovery and AI task execution. So our key idea is that we're going to design unified function for both tasks. And also we're going to design a gated net to control the output information bits to adapt to the variational channel conditions. So first, we use the idea of a data rate reduction together with the MSE minimization to get the unified loss function design. Because we consider two tasks, one is classification. So For classification, right? So we use the coding rate reduction. Okay, we just try to maximize the coding rate reduction to maximize the performance of classification. So the idea of coding rate reduction is that we try to make the data samples with the same class as compact as possible, and for the data samples with different class, we can separate from each other as far as possible. So that's the basic idea. And for data recovery, we use the MSE minimization as a loss function. So in order to accommodate the two objectives, we consider overall loss function, which corresponds to the weighted sum between the coding rate reduction and the MSE minimization. Okay, so we use this one as a unified loss function. And the second design is to adapt to variational channel conditions. So we use the gated deep JSCC. So we introduce a binary valued mask at the transmitter side, and accordingly we use a multi-layer perception. Okay, and accordingly we use the channel condition or the SNR or the noise power as the input, and the output the binary valued vector, which utilizes as a mask to determine the corresponding features to be transmitted. So we do some experiments to evaluate the performance of the JSCC design, and we compare it with versus various benchmark schemes. And we consider simplified tasks by using minist or handwritten digits as a basic model, and we also use real-world colorful images from CIFAR 10, okay, as a test data set. So for the numerical results, we just compare the performance versus the separate source coding and the channel coding, and also the deep JSCC with only considering classification task or data recovery task. So you can see that our proposed design can perform quite well in the pictures. So it can recover data quite well. And also we can look at the classification performance. Okay, so previous slide we showed the data recovery performance, and we can also look at classification. So for classification, right, we just use we just compare with JSCC with MSE only as a loss function. So JSCC with MSE is going to serve as a performance upper bound because it only considers one single task in this case, but our proposed design need to handle two tasks at the same time. So you see that our proposed design can outperform the benchmarks, and especially when the SSCC, the separate source and channel coding design, will face the so-called Kniff effect, which means that if the SNR become less than a certain threshold, its performance can become not acceptable. But you can see that even the channel condition is poor, our proposed design based on semantic communication or JSCC can still perform quite well. And also we just try to consider the effectiveness of the gated let to show the performance on the varying SNR conditions. So in this case, we're gonna train the model with fixed channel condition, but we're gonna implement the trained model on different SNR conditions. So you can see that in this case, our proposed design is actually quite robust against the SNR variation. So we can get some insight from our considered design. Okay, so far we just consider the vision tasks, but if we incorporated a wireless sensing, so how to do the joint wireless sensing and the semantic communication will be an interesting task. So in this case, we need to incorporate the design of the AI model for sensing together with the JSCC model to have an end-to-end model to perform the sensing communication and computation tasks. And furthermore, right, how to do the night weighting and how to design the adaptive semantic encoders by considering the resource limitation of edge devices is another important task. And the last one is actually how to exploit the night model. Especially for semantic communication, the night model can be used as universal semantic priors or the so-called semantic
knowledge base for edge sensing is also an interesting direction, especially in particular, right? People are interested in the so-called generative semantic communication. So I think large models can play an important role if we consider one sensing task. Okay, so let's do a conclusion. So the takeaway message for this talk as follows. So first point I want to make is that actually I believe, so we have done ISAC research for many years, right? Previously, we mainly focused on the model-based design or single processing-based design. And with the recent advancements of AI and especially the large models, how to integrating edge AI with ISAC is quite important, and it will be a key paradigm for our future 6G networks. And the second observation is that actually edge AI can enhance wireless sensing, ISAC, and the sensing assisted communication. In particular, right, we use LLM. It has the few short learning, robust cross-model capability, and improved generalization advantages. And also for learning, we introduce over-the-air federated learning to reduce the communication overhead. And we can jointly design the over-the-air computing with ISAC to realize integrated sensing, communication, and computation. And finally, for the inference task, we mentioned that we need to design the semantic communication, borrow idea from semantic communication to have a efficient edge inference. Okay, it can help us to reduce the redundant data and transmitting task relevant features only. Okay, so that's all my talk. Thank you very much. I'm happy to take any questions. Thank you very much.
Thank you, Professor Xu, for your very insightful and very fruitful lecture. We now have several questions from our online audiences. The first question is, LLMs are computationally heavy. When deploying them at the edge, how can we meet the millisecond level latency requirements of ISAC systems?
Okay, thank you very much. I think this is a very interesting question. So when we talk about to using large models for wireless systems, people always ask about this question regarding the latency and the computation cost. So I think actually in our case, we will not use the largest, so most advanced LLM model. So actually for our wireless tasks, we consider actually we use some, for example, the GPT-2, right? I think the model size is around several B. So I think that kind of model will be sufficient to our wireless sensing task. And also notice that, okay, so when we talk about latency, we're actually talking about the inference instead of training. And the training can be implemented offline. So the training and the fine tuning can be implemented offline. This means that the training latency is not an issue. And for inference, right, we can see that nowadays the base station and edge devices, the computing capability are increasing. So we believe that if we properly train the model and we do the, for example, compression and fine tuning of this model to reduce the size at the edge, so it is possible to realize such task subject to the latency requirements. Okay, so I think there are still many directions to go. For example, how to compress and how to prune the trained LLMs for edge implementation or wireless implementation. I think that will also be an important direction to go. Okay, thanks.
Yes, indeed. Yes, that will be a very interesting direction. Okay, the second question is, at the edge, can LLMs truly understand the physical dynamics of wireless channels better than traditional physics-based algorithms? For example, Kalman filtering.
Yeah, I think that's also a very interesting question when we talk about using no matter LLM or AI algorithms for our wireless communication, right? Because we have many advanced and well-established single processing methods, for example, Kalman filter, right? So I think the answer are following. So first, suppose that we we have a scenario that can be well modeled. So in that case, I think we can use the conventional single processing or, for example, Kalman filter, or maybe some optimization-based method to solve this problem. Because there is a performance guarantee there, right? We can know how much we can achieve the optimality. So in that case, I believe that there is no need to use AI algorithms or using LLM or any other kind of AI methods. But notice that when we talk about network sensing, right, and also different types of sensing tasks, the tasks are become more and more complicated, and also the scenario are becoming more and more complicated. For example, right, in the complex scenarios, it may be very difficult for us to model the exact channel model, right, or model the dynamics of the objects or devices in the environment. So it's difficult to model them. So in that case, I think we should rely on some data-driven approach to resolve this issue. So in this case, we consider this scenario. So it's data-driven, so it can perform quite well. But if you ask whether this one can really interpret the wireless environment, so I still don't know the answer yet. I think there are still many open problems there. And I think another interesting direction along this one is how to combine the well-established single processing method based on our models together with the data-driven approaches. I think that will be interesting direction to go. Okay, thank you very much.
Okay, thank you. Our third question and the final question is as follows. LLMs are designed to process discrete text tokens. However, CSI is a continuous complex signal. How do you actually tokenize or translate the continuous CSI data into an input compatible with the LLM during fine-tuning? Does this quantization or mapping process cause a loss of subtle signal features crucial for sensing?
Yeah, that's an interesting question, but it's true CSI is continuous, but notice that right in our modern digital communication, we always sample the signals into sample them, right? And also we also do quantization, right, for this one. So in our case, we just I think the key here is that we need to have some certain preprocessor and the feature extraction components to process the continuous CSI information to tokenize them as here. So it is an interesting question how the quantization level will affect the performance. So the answer, so I still does not know the answer. I noticed I remember that my students just I forgot what kind of quantization level they use, but it is true that you need to quantize the information. But I think the main idea why the LLM that is used for language, right, can be used for our CSI. So you can view both of them as time sequence, and this time sequence has correlation over time. So the LLM and the language model, right, the next token prediction is similar for the CSI prediction problem. So we try to predict CSI in the next time instant. So it's similar to the next token prediction. So due to this similarity, we see that fine-tuning LLM are quite useful for the channel prediction task. But if you try to utilize the fine-tuning LLM for other tasks, I'm not sure whether it still can perform as well as this scenario. And also, you can see that due to this reason, right? For this reason, in our wireless sensing task, we did not directly using the LLM for classification. Instead, we transformed the problem as a channel prediction problem. We just predict the CSI in the next time instant, and then we compare the predicted CSI feature versus the observed feature to get the classification or detection result. Okay, but how to do classification in this case and what is the performance? I'm not sure about that. Okay, thank you very much. I think that's also an interesting direction to study in the future.
I myself have a little bit question about this, because, for example, if you quantize the CSI vector, whether are you quantizing the CSI vector itself or quantizing its features?
Actually, I think when you input here, right? So the whole process, first we quantize CSI at the beginning, right? And then you process. This depends on the computation accuracy of your algorithm, right? You quantize here, and then you get the after you do the pre-processing, and then you have several channel attention layer and a cross attention layer, and then you fusing them together, and then you input them into the backbone LLM. So I think is we quantize the CSI here, and according to the whole process can output the feature. So there is no further quantization of the feature at this stage.
Okay, I see. Okay, thank you again, Professor Xu, for your very, very exciting and interesting talk today.
Okay, thank you very much, Professor Xiong.
All right,
Thanks.
so I guess it's all for today's presentation. Thank you very much for attending Charles Park course series. Let's see you next time.
See you. Bye-bye.